Buenas tardes. So I realized later that my title, Understanding and Communicating Uncertainty, could have a lot of different meanings, and it might be even the state of my marriage, or perhaps my bank account, but in fact, it's not. It's probably more interesting to you because I'm going to talk about rocks, and specifically, I want to talk about assaying. What I want to tell you today is that it may not be news to you, but it's a new way of thinking, and that's that every measurement has an uncertainty. And why I think this is important is that when we are making business decisions, we need to understand the uncertainty associated with the numbers that we're using to make important decisions, whether that's estimating resources, moving ahead with a mining project, and which drilling target we want to perhaps test from geochemical data. And so to try and demonstrate to you why this is an important concept is I want to show you a series of assays from one sample. Sample was taken underground at the Bulyanhulu mine in Tanzania. And I had the opportunity to do this project with Barrick's assistance, and we took 64 splits of the sample, and we did what's called a screen metallic gold assay, which is, one expects, one of the most reliable types of fire assay determinations for gold. And for the results, we had a range of values, and the values changed from 17 grams per ton to 115 grams per ton gold, and every single assay is correct. This is an example of a rather extreme sampling problem, and luckily for them, they have a lot of gold in their system, but still it proves the point that we need to be able to communicate the range of assays to each other when we're describing a number. So that's what I want to talk about today. I want to just introduce some concepts that are about how we can maybe communicate precision. This concept called the curved failure line for assays. The idea that all of the uncertainties are additive or cumulative, and then also talk about this concept that your data only has to be fit for purpose. Now, what I am going to talk about today is fundamentally the concept of precision. I want to separate this from the discussion about accuracy. And so maybe a lot of you who can remember as far back as an early chemistry class would remember the bullseyes that talk about the difference between accuracy and precision. However, I give this talk a lot, and quite frankly, the bullseyes are boring. I'm tired of the bullseyes. I've moved on to kittens. So, accuracy is when the kittens have all of the mittens in the same space around their paw. Precise can mean all the results are the same, all the mittens are in the same place, but they're not in the right place. If we have both good accuracy and precision, the kitten is wearing his mittens. And trust me, a lot more people remember the kittens than they do the bullseyes. So when we were talking about accuracy, we measure accuracy with things like reference materials or standards. We evaluate the results for our standards, and I would say certainly in the last 10 years, the industry has done a remarkably better job of implementing quality control programs that really focus and do a good job of looking at the accuracy. And I also believe we've seen a really incredible improvement in the quality of lab results now that we're all really watching carefully. And today, I would like to offer you, if you care to come by our booth, number 42, I'd be happy to talk to you more about the standards that we sell and also some ways in order to generate the quality control charts with a free QC macro. One of the things I see repeatedly, I read a lot of 43101 reports, is the discussion about the duplicates that we all are accumulating in our databases. And what we have in the industry is what we call rampant terminology, and we see people using indiscriminately a variety of terms around precision, absolute relative difference, percentage difference, a lot of different terms that have a mathematical significance and a lot of different synonyms. And in fact, what's important is I don't expect you to memorize all of these equations, but they actually are all very different. They have a very different mathematical meaning. And if we aren't all speaking the same language, we're really not going to be able to communicate on these meanings of precision and therefore maybe how to improve our systems. So I know that geologists, as a rule, hate things like mathematical terms, but I do just want to bring to your attention the main concept around precision, which is how likely am I going to be able to repeat a result? In my case, I'm talking about assays. So in general, if you are describing something with a 1 standard deviation uncertainty, you're saying that 68% of the time, you expect the results to report within plus or minus 1 standard deviation. If you talk about 2 standard deviations, you're saying that 95% of the time, results will report within those 2 standard deviations or 95%. If we say 3 standard deviations, it's almost 100% certainty that the results will report within that range. And what we're really saying when we want to communicate what the grade is for something is what we need to be telling people is not just the grade is 100 grams per ton, but also something about the precision, about the reliability, about the probability of being able to repeat that assay. And one of the ways to do that is to say the precision, the 2 standard deviation precision, is 10%. But what that means is that 95% of the time, that relates back to the 2 standard deviations, 95% of the time, I believe if I re-assay that sample, I'm going to get somewhere between 90 and 110 grams per ton. And we should not be expecting to get exactly the same number every time we subsample a material. In particular, the more coarse it is. So we are more likely to be able to repeat an assay, for example, on a pulp than on 2 halves of the drill core. And the other issue that I see confronting us as an industry is a problem, again, of communication, but this time between the chemist and the geologist. And in fact, it's about the meaning of the phrase detection limit. Detection limit to a chemist means that I can just begin to see the signal from the noise. But what the chemist understands is that the results that are close to detection limit, even 20 times detection limit, still have very poor precision. And it's only until you're at least 20, if not 50 times detection limit, then you can start to achieve the kind of precision, the reproducibility, that is optimum for that analytical method. And this is true of all analytical methods. So, I'm going to try and explain this graph in 30 seconds or less. It was supplied to me by ALS, and thank you very much for that. And so the precision is shown on the y-axis from 0 to 100%, and we have on the x-axis the gold concentration on a log scale. But the most important thing to note is that the curves are very steep, near vertical, as you approach the detection limit. By definition, at the detection limit, precision is worse than 100%. It will quickly improve, and this is the case for fire assay, to the optimum, which is about 7 to 10% for the analytical method when you're at much higher concentrations. So if I use the example of the orange line, the one furthest to your left, the detection limit is 1 ppb. The precision is very poor, all the way until I get to at least 0.05 parts per million, at which point it starts to approach 15% and then eventually becomes the expected plus or minus 7%. And I implore you to remember these detection limits are, and this precision is based on analyzing very fine-grained and homogeneous materials. This is just the analytical error and does not include at all the sampling error. And one of the reasons we want to think about this is where, for example, does our cutoff grade fit in this curve failure line? So in my little cartoon here, if your cutoff grade is in the range where that curve is starting to get very steep, you likely have very poor, you're very unlikely to effectively discriminate ore and waste. Now this is another related idea, which is the propagation of uncertainty. And what this means is that all of the uncertainties, what a chemist is happy calling an error, are additive. So when we look at something like core duplicates, right? So we've split the core in half, and we look at the results for the two halves of the core, and we see they're very different. What we're really looking at is the sum of the errors associated with the analytical method, taking 50 grams, for example, of the pulp for the fire assay, that's a subsample, taking 250 grams from the crushed material that we pulverized, and then we also have the splitting, taking two halves of the core, and we also have the geological uncertainty, right? We have that issue of the material that we're sampling is not homogeneous. And all of these things are additive. And the reason this is important is that if you decide you want to fix something like your sampling your field duplicates, RC duplicates, splitting the core, etc., you need to understand all the parts of where that total uncertainty comes from or where that total error is situated. I'm going to throw this idea out, which is that variance is additive, only to discourage you from trying to do things like averaging relative standard deviation. I'd now like to show you a series of slides of graphs that are generated for a specific project in order to show that there are different ways of communicating around this idea of uncertainty. This is a project from Canada, which is a low-grade gold deposit. These are the pulp duplicates. All laboratories report about 1 in 20 samples as duplicates, and a very simple XY plot. So the original gold versus the lab duplicate, and they're perfect. So we have no further discussion. However, if I now plot that on a log scale, because a lot of these results lie between 0.1 and 1 gram per ton, we'll actually see there is some noise associated with doing a duplicate pulp. And another way of showing this data that I find quite useful is as follows. It's called a relative percent difference graph. On the y-axis, we just take the difference between the original and the duplicate and divide by the average. And we plot that against the gold result. Now I see quite a different pattern. Maybe you see it too. So what I see is that above 0.1 grams per ton, I actually have 95% of the samples report within 10%. Oh, well, that's actually pretty good because that's what we expect for the fire assay. But you'll see less than 0.1, it gets a little hairy. In fact, most of the results, I guess you can't read them that well, but all the results, if there was no difference, would lie on this 0 line. But instead, what we see is a lot of noise, up to plus or minus 60% as we get close to the detection limit. I see a curve. I see something that swings up and across, and that's related to this problem of the analytical method having a curve failure line. It is not related to sampling or anything that was done improperly in the sampling or the assaying. Now, this is a particular case where the client was using a 250-gram pulp for a gold project that obviously had a few issues around getting a representative sample. And so here I've plotted, again, the results the lab provides you for the 250-gram duplicates, and I've put the blue box on that shows the plus or minus 10% that we had for the pulps, and now you see the orange box, and that is showing you where 95% of the samples fall within actually plus or minus 40%. So we don't really have a problem sampling the pulps, that's plus or minus 10%, but when we take a 250-gram split of the original drill core sample, we now know that we have quite a bit of uncertainty at that stage, right? The stage where we're riffle splitting from the original entire sample being crushed and taking 250 grams. So I said to this client, you know, a lot of gold projects use a much larger pulp, and they would use one kilo and not 250 grams. And they said, fine, we'll do that. I said, well, we could do some testing. No, we're just going to go ahead and make that change. So the same project, the next phase of the drilling program, and we now are using the same lab, but we're using a larger pulp. So the results are really quite comparable. And in this case, there was no difference whatsoever. So it didn't matter if you used a 1,000-gram pulp or a 250-gram pulp, you essentially had the same uncertainty. So this means that there really was no value in paying the extra money to move to the larger pulp. Probably a better solution would be, there are some other options at most commercial labs, and that might be crushing the sample to something like 90% passing 2 millimeters instead of 70% passing 2 millimeters, because that would give you a finer crush that would be easier to subsample. And then the other possibility is moving to something called rotary splitting as opposed to riffle splitting that also has better sampling characteristics. But my real point is that if you don't measure it, you can't fix it. So you don't know you have the problem until you actually make some very simple charts, all of which can be done in Excel or Fusion or whatever other software you want to use. And it's data that are readily available and already reported to you. And it isn't the same for every project. And my other important message and why you have to measure it for your project. Not all projects are the same. And so this is another project in Canada, also a similar mine grade of around 1 gram per ton. And I'm still using the relative percent difference graphs. And again, I have relative percent difference now from plus 200 to minus 200%. It's very noisy. And the grades from 0.1, this really doesn't show, from 0.1 to 1 gram per ton are about in the middle of that graph. You'll see again the way it flares out as you approach the problem of the lower detection limit and the problem of the curve failure line. In this case, the pulps only repeat within plus or minus 40% for 95% of the samples. Before we had plus or minus 10% on the pulp, now I have plus or minus 40%. This is a particularly difficult project in which to get a representative sample, even subsampling the pulps. And then if you looked at the preparation duplicates, using a 1,000-gram pulp, even if you're using a large subsample, you move to precision of 60%. But now you see you've gone from 40% in the pulp to 60% by taking the subsample. It's the pulp that's the problem. It's not the size or the size fraction of the crushed material. So guess what? If you don't measure it, you can't fix it. but it's got a different fix for this project. For this project, you most likely might, I mean, one of the few actions you could do is something like a screened metallic, right, where you screen the entire pulp and you assay all of the gold that's, all of the material that's in the plus fraction, including what you were assuming is the coarse gold. And what you really want to do is don't have a gold project. Because if you are looking at something like copper, it's different again. And in fact, now my scale on the y-axis for the relative percent difference is plus 20% and minus 20%. And the pulps and the preparation duplicates more or less repeat within 5%. It's just not the issue. Now, if copper were the same price as gold, we would probably be finishing the conversation here. There are many times where we're using geochemical data, assays, and I'd like to say to you, this also applies to a certain extent to geophysical data, but with geochemistry, it's only with geochemical data that we're actually monitoring things like accuracy and precision. And I want to give you an example within the exploration industry. And so this is really a thought experiment. The idea is perhaps I've taken a line of samples, of soil samples, and on the x-axis in the line graph here, the x-axis is some distance along the traverse. And the y-axis is some measurement, copper, zinc, thallium, whatever you want on the y-axis. And what we did for this is we had real data for the blue line, and we used the random number generator, and we added plus or minus 50% error, which is not that uncommon for a project thing like soil sampling. And if you think about then projecting that onto a grid, for example, we had multiple lines, line profiles, you would then look at the figure on the lower left-hand corner, which is kind of a typical, drill the bright red dots. And so we have two very nice anomalies on the lower left-hand side. But if you have a lot of noise in your data, for example, plus or minus 50%, you would end up with the figure on the right-hand side, which is the same data, plus or minus 50%. You still have your anomalies. You still have the two bright red drill targets in the upper left-hand side, but you also have another series of anomalies. They're not anomalies, they're false anomalies, and you don't want to have to drill those. You just need to know that there's the possibility of this kind of noise in your data set in order to be able to interpret it. We need to understand precision, we need to measure it, we might be able to fix it sometimes, but we need to know these things when we're evaluating geochemical anomalies. We need to know it when we're just trying to discriminate ore and waste. We're going to encounter these issues when we're trying to establish where there's a bias between data sets, and that can include things like, are my diamond drill hole data different than or biased relative to my RC holes? Some really basic questions we're always asking ourselves. I just showed you a couple of simple examples around how to select sample preparation protocols to maximize effectiveness and potentially control costs to get you the best possible data. My current concern is that I hear a lot of talk about big data and data analytics. And we have a number of situations where we've had big contests and million-dollar prizes for someone to run data through algorithms. And I will tell you that if the data aren't good quality, we are going to have the problem of garbage in and garbage out. That's the only thing that's guaranteed. So I, again, just encourage everyone to think about the quality of their data, not just through the use of reference materials, although I'd love to sell you reference materials, but also in terms of that uncertainty. We really want to think about when we select an analytical method, Are we choosing the right method with the right detection limit for our project? We really want to understand if we have measured precision properly and if we have communicated it to the people that we're working with effectively. And I guess the one last item that I really want to emphasize today is that all of the errors associated with handling your samples from the time you take it out of the ground until you get an assay value on a certificate, all of that is cumulative, and we will do a much better job for ourselves, for our targeting, for our shareholders, if we have some control on all of those, on all of that data. So, thank you very much.